Hello, good day. This is Engineer Rodolfo B. Ocati from Haro, Iloilo City, Philippines. These are my topics scheduled for series of session. Today I will have this fourth session, the three moment equation given this two span loadings, uniform load and triangular load distances 2, 6 and 4. This is the basic equation of the three moment equation. Okay, M1L1, this is the moment on the left of this BCD. Now this three moment equation uses the two span at a time when we analyze this. So we have two unknowns, C and D. The moment at C and moment at D are the unknowns. So when we have two unknowns moment, we usually have two equations, and when we take the one equation, so that you consider two span at a time, BCD is 1, then the other equation is that we create imaginary span dy. So we have two span again, CDY, where the right portion is imaginary. We create equation here. Now it is a requirement to, in order to solve this three moment, that the area here is found in this figure, area 1. The area 2 is this one. Now first we have to know how to solve this data 36, 16, 16. Okay, first consider BC, span BC as a simple beam. I will solve the reaction here. RB and RC are equal. It is equal to half of this load. So total 2 times 6 is 12. RB is 6. RC is 6 kilonewton. Okay. Now 6 reaction RB 6. If you make a moment going to C, where C is the pivot, so reaction RB of 6 multiplied by 6, we bring this reaction RB to C. So 6 times 6 is 36. Down below here we have this is the result of the moment by parts due to uniform load of 2. So we bring all this uniform load to pivot at C. Remember, this is a simple beam. AB does not exist, CD does not exist, only simple beam BC. So the moment due to the uniform load going to C is 2 times 6 times 3 from the center going to C. So 2 times 6, 12 times 3 is 36. These two, positive and negative, must be 0, because the moment at C for a simple beam, there is no moment at C for a simple beam. The other side on the right, consider this as a simple beam CD. So usually the reaction of D is twice the reaction at C. The total weight here is 1/2 6 by 4 is 12. Okay, total weight. 1/3 of that goes at RC, 2/3 of that goes to D. So total weight 12, 1/3 of that is 12 divided by 3 is 4. So the RC is 4. Bring that here, 4 times distance. So 4 times 4 is 16. The triangular loading created moment by parts is at third degree because of triangular. The total weight here is 12. Then distance is 12 times 1/3 of 4. The distance 1/3 of 4. So 12 times 1/3 of 4 times 4 is 16. These two must be also equal to 0. Okay, so we need this to solve this 2. The left one is this one, the right one is this one. Okay, now 2 span at a time, so you consider BCD alone na, BCD excluding AB because we are considering BCD only. So on the left, the true moment at B is 2 times 2 times 1. This is the actual moment at B. So 4, the moment at B is 4 negative times 1 minus 4. Then the left span is 6 1. Then twice the moment at the center moment of BCD is C. Twice moment at C, then sum of span 1 and span 2, 6 plus 4. Then this one is the moment on the right. Moment at B times 4. L2 is the right span. Then for the constant on the left, 6/6, this is the left side of 2 span. Then the area, okay, the area is 1/2 area of this 1/2 36 by 6 times the distance of 2/3 of 6. The origin of the distance here of the left moment by part must be on the left. Okay, now this lower portion negative second degree 1/3 36 by 6 times distance of 3/4 of 6 3/4 of 6. Okay, now because this is 2 span, the first span is this one. The second span, this one. The second span, 6/4, this one. 6/4, the area here, triangular loading 1/2, 16 by 4 times the distance. The second right moment by parts, the origin of the distance must be also on the right. Distance must be on the right. So 1/2 16 by 4, 1/3 of 4. It's 1/3 of 4. Minus this negative third degree curve. So minus 1/4, 16 by 4. Distance from here up to the centroid is 1/5. Okay, 1/5 of 4. Then solving for this is 10 times 2, 20 mc, 4 md. The constant minus 128. If you solve this must be 128. This is positive, this is negative. Okay, be sure to check, include this one. Oftentimes student misinterpret the result because this one is excluded, so be sure to include this. So the constant is minus 128.8. Negative because usually the moment at C is negative. The moment at D is usually negative. So these two are negative and the constant must be negative. Okay, this is equation 1, BCD. The next equation is to span CDY. Only that dy is imaginary. Okay, we create another equation, CDY. So consider the span CDY. Again, we use this equation, CDY. Moment at C is unknown. The left side, the distance is 4. Distance is 4. The middle moment is twice moment at D. Then the distance L1 plus L2 is 4 plus imaginary 0. Then the moment on the right of CDY, but the moment at Y is 0. So no moment my. Then the constant here, 6 over L1. This is the left span of CDY. 6 over 4 times the area of this. 6 over 4 times 1/2 16 by 4. Remember, this is the left side of CDY. So the origin must be on the left. So 2/3 of 4. The distance from here up to here is 2/3 of 4. Then the lower part is 1/4. So 1/4, 16 by 4. The distance is 4/5 of 4. From here up to here, 4/5 of 4. Then the secant span of CDY is 0. There is no area, so 0. Solving this, 4mc, 8md, all of this constant, the sum of this in this is positive, but you transfer that to the right. And it becomes negative minus 51.2. So equation 2, these two, equation 1 and equation 2, solving by simultaneous equation, MC becomes minus 5.7333. MD is minus 3.5333. Okay, so moment here is now solved. Moment C, moment D is solved. Moment B is minus 4, negative. Negative moment, negative moment, negative moment. All three are negative moments. Now the reaction, okay, RB. First I will bring this drawing. I will bring this drawing here down below. RB, okay. Bring nearer to the solution. Okay. This figure above is the same as this one. So consider span ABC cut here. Consider the left portion of the cut section at C. So the figure is only ABC. Then there is a moment here as clockwise moment at C minus 5.733. If you place the direction arrow as clockwise here, do not place the negative, just 5.733. It is understood to be negative, but do not place the negative here with the arrow direction as clockwise. Okay, so moment at C, solving for RB. 6RB, this is 6RB is equal to, okay, this is clockwise, uniform load, equate that to, place that to the right of equality. This is positive, we transfer that to the other side of equality. RB times 6 is equal to 2 times 8, 2 times 8, the whole. 2 times 8 times 4, the middle, times 4. Then, since there is a moment at C, this is opposite with the direction of the uniform load. The moment at C is negative, opposite with the uniform load. Okay, the equality here, so we can solve RB as 9.711 kilonewton. Okay, now RB has the actual value of positive 9.733. I want to solve RC. Take the whole beam, then take moment at D. There is a moment at D of 35.533. direction is clockwise here. Okay, take moment at D. RB given as 9.7111 times 10. This is 6 and 4, 10. Then plus 4RC. This is 4RC. Direction like that, direction like that. Then equate that to the counterclockwise direction. This is equal to 2 times 8. Again, the moment must be pivot at D. Moment at B. 2 times 8, half of 8 is 4. Distance is 4 plus 4. Then this triangular load, 1/2 6 by 4, distance is 1/3 of 4. I take moment at D. 1/3 of 4. Then there is a moment at C, which is opposite with the uniform load, triangular load. Direction is clockwise, while this one is counterclockwise. So negative, opposite with this. Okay. So solving for RC, we have only one unknown. RC is 10.8389. Okay. Then solving for RD, going up RD here, or reaction at D. Consider the right of the cut section CD. You cut here, then there appear the moment at C as counterclockwise of 5.733 counterclockwise. Okay, solving for RD. RD times 4 is equal to opposite direction 1/2 6 by 4, 6 by 4. Distance from C is 2/3 of 4. And there are two moments that involve here, moment at D and moment at C. These two moments are different direction, clockwise, counterclockwise. So moment at D is the same direction as the triangular. This is clockwise, this is also clockwise with respect to C. Okay, these two. Moment at D is the same rotation as with this. So this is this one. Moment at D is 5.533 positive, the same direction as this one, while the moment at C is opposite as with the moment at D. So minus 5.733. Okay, I hope you don't confuse. Okay, solving for RD, it is 7.45 kilonewton. Now we have solved now RB, RC, RD. These three, if you add these three, must equal to the total external load. This 16, and this is 6 times 2, 12, 16 and 16 and 12. So check that with your calculator. Now given now the three reactions, we can draw this shear and moment diagram. This is the shear diagram given that 3 forces, 745 is RD. Okay, and moment diagram will look like this. Parabolic here, while here 3rd degree. Okay, this topic, the discussion of this is under the strength of material. So I will not discuss this in detail. that conclude now the discussion on how to solve this beam. Now for you to practice, I have here example problem. Replace W1 by 4. Instead of 2, you replace this by 4, and instead of the other one, replace that this 6 into 8. Then solving for the moment by parts, instead of 36 and 16, the answer is 72 and 21.33. Then the moment at C is this one, the moment at D this. The three reaction RB, RC and RD. Okay. That is example 1. Example 2, the same. Replace W1, W2, then the distances, replace that also with this. Answer this one. Okay, be sure to subscribe. That's all. Thank you.